Hi everyone, welcome to all of you on my YouTube channel. So I'm Ankit Mishra. I am continuously making video of PYQ series, and here I was starting the PYQ series for the second part of the distillation mass transfer operation. So here you can see the question says that a distillation column with N plate is being operated in a normal condition, right? So you have a distillation column here, and at the top of the distillation column we have to have a condenser. Sorry. And in the bottom of distillation column you can see there is a reboiler, and this one is feed, and this one is D, and this one is the bottom product. So it is saying that the operation is shifted to total reflux condition at the new state condition. So when total reflux condition is there, when then are tending to infinity, right? Reflux tending to infinity. So in that condition what will happen, you can see that the top and bottom composition correspond to the maximum enrichment is achievable, right? Why? Because whenever it is going to shifted towards the total reflux condition, then definitely you can see that more volatile component which is there in the liquid phase will be start coming more and more into the vapor phase. So that's why you can see that the top product will be having a maximum concentration of more volatile component, and bottom product will be having a composition of very less volatile compound. So you can see that both the top and bottom composition correspond to the maximum enrichment is available. So from here your option D will be correct. Now moving towards the next problem, and here you can see the question says that an aqueous solution of methanol is to be distilled in a tray column. High pressure steam is available as a resources of it. For a given reflux ratio and overhead composition, two options are available. One, a reboiler is used, and no reboiler is used, and a steam is fed directly. So when we see a normal distillation column, it looks like that, and in the bottom you can see there is a reboiler, right? So this reboiler is heating the bottom product, and it is going like that. And when there is an open steam condition, so here from the bottom reboiler is being removed and directly open steam is being fed, something like that. So here S is there, W is there, like that, right? So these two conditions, first condition is there and second condition is there. So based on this condition you have to understand the option that as correspond to option first. In option 2, less number of trays are required, composition of the residue remains unchanged. More number of trays are required, but the residue composition remains unchanged. More number of trays are required, and residue composition is more diluted in methanol. So if you see the if you are going to use the open steam condition here, so you will be able to see that more number of composition of so obviously when open steam is used, then number of trays required stripping section decreases. So if number of trays required in the stripping section decreases, so total number of trays will be equals to number of trays required in rectifying section plus number of trays required in the stripping section. So if it is decreasing, then total number of trays required will be decreasing, right? But number of trays required in rectifying section will be fixed as it is. So you can see number of trays required in stripping section will decrease. So from here you can see that composition of the residue remains same, less number of trays are required. So less number of trays are required. So here in option they can give you that less number of trays are required in the stripping section. That option will be also correct, but here they are, the gate has asked gate has given you the option in terms of the total number of trays. That's why your option will be correct. Okay, now I'll be moving towards the next problem of today's discussion, and here you can see that a distillation column at a plate point is sealed up by 3 times for the industrial use at a steady state. After scaling up, then number of theoretical trays increases by 3 times. Number of the minimum reflux ratio is increased by 3 times. The feed flow rate and the product flow rates are increased by 3 times. The feed composition and product composition are increased by 3 times. So when we are increasing or when we are scaling the distillation column, so during the scale up, so let's say here scale up is being done up to 3 times. So you will see that number of theoretical stays, that is wrong. the minimum reflux ratio is increased by 3 times. That is also wrong, that the feed flow rate and product flow rate are increased by 3 times, right? So I think this is the correct option, because you have to increase the feed flow rate and product flow rate, right, till 3 times, because you are scaling up means you are increasing the diameter of the column, right? So it will give you a flexibility that you can increase the feed flow rate and product flow rate also. So this is being done to increase the production rate of the product. Now moving towards the next question, the question says that in a tray column separating binary mixture with non-ideal acids, one of the following statements are correct. Point efficiency can exceed 100%. This is wrong. Mercury efficiency cannot exceed. It is wrong. Mercury efficiency can exceed 100%. This is right. And but mercury and point efficiency can exceed 100. No. So only mercury efficiency can exceed 100%, and point efficiency cannot increase 100%. Is that clear? Now moving towards the next question, the question says that for a two-phase feed where 80% of feed is vaporized under column condition, the feed line slope is. So when we talk about the feed line equation, so feed line equation used to be equals to Q upon Q minus 1 into X minus ZF upon Q minus 1. So where Q is called as the condition of feed, and obviously XZF is called as the feed composition. So here you can see that the Q is equals to fraction of feed is in the liquid form. So if you see from the data that feed 80% of feed is vaporized, so 80% feed is in the vapor form. So how much feed is in liquid form? 0.2% means 20%. So your Q will be equals to 0.2. And what is the slope of Q line here? Slope of Q line, or Q line is also called as the feed line, that is equals to Q divided by Q minus 1. So if you will substitute this thing, 0.2 divided by 0.2 minus 1 minus 0.2 divided by 0.8, so that is equals to minus 0.25. so slope that is equals to minus 0.25. Is that clear? Okay, so with that we got the answer, that is minus 0.25. Your option A will be your correct option, that is minus 1.1 by 4. Okay, so after that we'll move towards the next question. The question says that a liquid mixture of benzene and toluene is in equilibrium with the vapor at 101 kilopascal and 373 Kelvin. The vapor pressure of A, let's say I am assuming A is your benzene, 156 kilopascal, and B is your toluene, and that is given as your 63 kilopascal, and assuming that the system always rolls slower than mole fraction of benzene in the liquid phase. So you are supposed to calculate what is XA. So if you write Y into PT is equals to XA multiplied with PSA, okay, and Y1 Y, and again YB is equals to YB into PT, that is equals to XB into PB set. So if this one is equation first, this one is equation second. So if I'll add equation first and second, we can get PT is equals to XA PA set plus XB PB set. So from here I can write PT is equals to XA PA set plus 1 minus XA PB set. So the value of PT is equals to, if I take common XA, so I can write PS set minus PB set plus PB set. So here you can calculate XA will be equals to PT minus PB set divided by PS set minus PB set. So here from the questions you can see the PA total pressure is 101 and the PA set is 156, PB set is your 63 kilopascal and PA set is 156 minus 63. So once you calculate, you can you will get mole fraction of A, that is benzene in liquid phase, that is 38 divided by something like that. So I think it would be approximately more than 0.5. If you'll see the option, you can say that you'll be getting answer is option A. Okay, so with that we'll move forward towards the next question. The question says that separation column of vapor liquid contact process is 200 kilomole per hour of vapor. So the mass flow rate of vapor, that is equals to 200 kilomole per hour, and the flooding velocity UF, that is given as 3 meter per second. The column operates at 85% of the flooding velocity. So the operating velocity of the distillation column is equals to 0.85 of U flooding, right? Next is the downcomer area is 10% of the total cross sectional area. So if I am assuming a downcomer, that is equals to 0.1 multiplied with a cross section. And what is a cross section? That is equals to pi by 4 diameter of tower whole square. So if I want to write mass flow rate, I can write density multiplied with area of cross section into velocity, U operating velocity, right? But here you can see mass flow rate is given 200 and kilomole per hour. So I can convert into 3600, that will be into kilomole per second, right? And that is density of vapor is also given, that is 2 kg per meter cube, 2 kg per meter cube, but you have to convert this density into molar density and you have to divide by 44, then it will get converted into kilomole per meter cube, and multiplied with area of cross section is equals to 0.1 multiplied with pi by 4 d square, and again the velocity is equals to 0.85 multiplied with your flooding velocity, so 3. So when we do this calculation, so you will be getting, and you are supposed to calculate the diameter of the column here. So this is just a simple mathematics. From here you can calculate the diameter of the column. So that is 200 divided by 3600 multiplied with 0.85 into 3 into 44 multiplied with 4 multiplied with 2 into 0.1 into pi, which is equals to d square. So finally you will get the d value, that is equals to root over 200 into 0.85 into obviously 44 into 4 divided by 3600 into 2 into 0.1 into pi. So after doing this calculation, you will be getting the value of diameter of the column, that is equals to 0.82 meter. Okay, so this was just a question that has been asked from distillation column to calculate the diameter. So this is the problem of designing of distillation column, and while you changing the cross sectional area, operating velocity, flooding velocity, all of these things, you can change the diameter of the column also. That is very important thing. So after that I'll be moving towards the next problem, and the question says that 100 moles of binary mixture of F. So let's say you have a batch distillation unit here, something like that. Okay, and in batch distillation unit 100 moles of binary mixture F was there. So let's say F was 100 moles initially, and 40% XA was your 0.40, let's say XF. The composition of heat is given XF, and treated in the batch distillation unit. After 1 hour, 70 moles of the distillate D is collected. So D was 70 moles, and the relative volatility alpha is also given to you too. The governing equation, that is this equation is called as the Rayleigh's equation for the batch distillation rate. So you are supposed to calculate the average mole fraction of A in the distillate is, right? So let's try to calculate this thing. So what is the average mole composition of distillate? So you are supposed to calculate the value of XW here. So from the formula, if you see, log F into XF divided by W into XW, that is equals to alpha log F into 1 minus XF divided by W into 1 minus XW. So if we calculate these things from here, that F is given, XF is given, and distillate composition is given. Distillate is 70. So what is W? W will be equals to your 30. Is that clear? So now I'll be writing this thing. So you can write log F is 100 multiplied with 0.4 divided by W is 30 multiplied with XW, we don't know, that is alpha is 2, and again log F is 100 multiplied with 0.6 divided by W minus W into XW. So W is your 30. So I can write 30 minus 30 xw, and you are supposed to calculate mole fraction of A in the distillate. Is that clear? So directly we can calculate W from here, and yeah, so this one is just you can write log 4 divided by 3 xw, that is equals to log 60 divided by 30. Yes, yeah, just 1 minute. So finally I'll be getting 40 divided by 3 xw, that is equals to whole square, right? So based on that we can calculate the value of xw from here. Okay, that's it.